Evet, geçen hafta arkadaşlar interrupt'lardan bahsetmiştik. Aslında bir tane interrupt'tan bahsetmiştik. O da teletype output interrupt'ımız. AH'nin içerisinde E varken gelen TNH interrupt'ı teletype output demekti. Bu da zaten ekrana çıktı aldığımız interrupt'ı. Neyi çıktı alıyordu? AL'nin içerisindeki değerin ASCII karşılığını ekrana çıktı alıyordu. Basitçe şöyle bir kodu vardı hatırlarsanız. Load effective address diye bir değişkenimiz vardı. Instruction'ımız vardı pardon. Bu instruction değişken tanımladığımız değişken yerini bulmamızı sağlıyordu bize. Bir register'a yüklüyordu o değeri. İşte karakter diye bir değişken tanımlayıp define byte keyword ile tanımladığımızda bunun memorideki yerini bize çözümleyip offset değerini mesela bx'in içine atıyordu. Sonra bx'i biz parantezler içinde kullanabildiğimiz için ekrana yazdırmaya başlayabiliyorduk falan filan. Üçüncü soruyu size ödev olarak vermiştim. Hani yapmaya çalışan yapmaya çalışsın. Bir puanlama falan olmayacak ama elinizi kirletirseniz iyi olur demiştim. Lowercase verilen herhangi bir karakteri uppercase'e çevirecek. Onun dışındaki hiçbir karaktere dokunmayacak bir programdı ödeviniz. Kaydı tamamlıyoruz. 4 kişi olmuşuz. Tamam. Ben direkt size cevabı açacağım. Cevaptan anlatarak gideceğim. Şimdi burası data segmenti ayarladığımız, DS'yi 100H yaptığımız, zaten default değeri de bu. O yüzden boş verin burayı. Değişkenimiz var. İsim adında bir değişkenimiz. Define byte olarak tanımlanmış. İçerisine irili ufaklı karakteri olan isim yazılmış. Sonuna da 0 null değeri eklenmiş bir değişkenimiz var. Bize ilk karakterin adresini veriyor. Değişkenimizin adres çözümlemesi. Değişkenimizin adres çözümlemesi bize ilk karakterimizin adresini verdi. Offset'ini verdi. Bx. Şimdi bunu ekrana yazdırmak istiyoruz ama hepsini uppercase'e çevireceğiz. Bir döngü lazım. Sonsuz döngü. Bu sonsuz döngünün içinden bir şartla bir karşılaştırma sonucunda çıkacağız ve return to operating system interrupt'ımız, yani aslında burası red kısmı olacak. Ekrana yazdırmak için AH'nin içerisinde E olması gerekiyordu hatırlarsanız. Başlangıçta E'yi koyduk AH'nin içerisine ve döngümüze bakıyoruz. Bu sırada bir ASCII table açsak iyi olacak. Evet. Şimdi Bx bize ilk karakterin adresiydi. Bx'in olduğu değeri getir AL'nin içerisine al dedi döngünün içerisinde. Ekrana yazdırmak için AL'nin içerisine koyuyorduk hatırlarsanız. Gelen karakter 0 mı değil mi? Bu bitiş şartımız. 0 geldiği zaman yazdırma işlemini bitireceğiz. Bunu da compare ile yapıyor. Compare birinci karakter operanttan ikinci operandı çıkartıp flagleri değiştiriyordu hatırlarsanız. Compare işlemini yaptıktan sonra eşitse flag'ini kullanan bir jump olan JE'yi kullanmış. Jump equal, yani AL 0 ise jump equal atlayacak. Nereye? Bitişe. Yani şu iki şart bitişi kontrol eden şart. Diyelim ki AL 0 değil bir karakter içerisindeyiz. İçerisinde bir şey olan bir değer var. Karşılaştırıyoruz. Ne ile neyi? AL'nin içerisindeki değerle 97'yi. 97 ne? Şimdi ASCII table'a bakın arkadaşlar. Şöyle zoom yapayım. Bakın 97 küçük A karakterinin başlangıcı. Yani küçük karakterlerin başlangıcı 97. Karşılaştırma yapmışız 97 ile ve neyi kullanmışız? Jump below. Yani 97'den küçükse demişiz. 97'den küçükse ne demek? ASCII table'ın dokunulmayacak tarafı. Yani zaten büyük karakterler ya da karakter olmayan diğer şeyler dokunulmayacaklar. Biz sadece lower case'leri upper case yapacağız. O yüzden nereye atlıyoruz? Below'sa jump, below'sa jump. 97'den küçükse yazdıra atladık. Yazdırımızda burada bir sadece ekrana yazdıran, AL'yi yazdıran bir şey ve BX'i arttırıp döngü başa döndü. Döngü başa döndü. BX'imiz artmıştı. Bir sonraki karakteri aldık. AL'nin içerisine. Kontrol ettik. Gelen karakter 0 mı diye. Hayır 0 değil. O yüzden atlamadı. Tekrar kontrol etti. 97'den küçük mü diye. Hayır 97'den küçük değil. Küçük B geldi. Bu da atlamadı. Tekrar kontrol ediyoruz. 122 ile. 122 neymiş arkadaşlar? Z karakteri. 122'den büyük mü diye kontrol edeceğiz. 122'den büyük olanlarda bir şey yapılmayacak olanlar. Yani 122'den büyükse de bir şey yaptırmıyoruz. Ekrana yazdırıyoruz. 97'den küçükse de yazdırıyoruz. 97'den küçük değil, 122'den de büyük değilse ne yapıyoruz? Bu aralıktaki değerler olmuş oluyor. Sadece küçük karakterler kalmış oluyor. O zaman 97, 100 bu aralıktaki değerlerden sabit bir değer olan 32'yi çıkarıyoruz. Neden 32? Çünkü fark hep 32. 97 eksi 65 32. İşte 110 eksi 78 32. Yani küçük karakteri büyük karaktere çevirmek için 32 çıkarıyoruz. Çıkarma işlemimiz de burası. AL'den 32 çıkarıp AL'ye geri yazdığımız zaman sonrasında buraya tekrar giriyor yazdırma kısmına. Ekrana büyük harflerle yazmış oluyor. Ne verildiyse değişkenin içerisinde. Mesela değişkenin içerisinde virgül, ünlem, bire gibi başka karakter olursa ne olur? Biz sadece küçük karakterlerin olduğu kısmı alıp gerisine hiç dokunmadığımız için o karakterleri olduğu gibi ekrana yazar. Küçük karakter geldiğinde de büyüğe çevirir. Sadece küçük karakterleri de değişme yapar. Evet. Burayla ilgili sorusu olan var mı? Bu geçen haftanın son sorusuydu. Yoksa bu haftaya başlayalım. ASCII Table ile işimiz bitti. Geçen haftanın şeyle işimiz bitti. Evet, bu haftadayız. Okay, my friends, let me switch into English. From now on, the assignment 8 is about shifts. Shift left, shift arithmetic left, shift right, shift arithmetic right is all this week we are going to cover. But before that, let me explain the left of the weeks. The exam week, the final exam week is between 7 June to 20 June. So our lesson, our last lesson will be in 3rd of June. We have 1, 2, 3, 4, 5, including this week. We have 5 weeks. 1, 2, 3, 4, 5 weeks to cover. So everything looks fine so far. Let me look at. Oh, one of them is in the holiday. This is Bayram. Anyway, we will cover the exercises within those lessons. Okay. This week's shifts. Please remember, whenever we see a new instruction, we open the help, go over the instruction sets, and look at the new instruction, which is shift left. Shift left can take memory and register, which is going to be shifted, and an immediate value. For example, shift left AX 3 times. This is going to shift AX 3 times. Or shift left 1000H memory address by 3 times. This is memory immediate. This is register immediate. This can be hexadecimal, can be binary, etc. Let's say decimal this time. But also you can use CL, only CL, not any other register, only CL. Let me put 4 in CL, and I'm going to use shift left with CL. Sorry, CL. I'm going to put 3 in CL, and I want you to see the result of this code in here. For example, shift left AX 3 times. This line split into 3 because shift left in actual assembly language can only be used with 1 operator, but our emulator can understand and resolve this into this. For example, if I write 10 in here, it will emulate into 10. Okay, so be careful. This is only acceptable in our lab session. In theory, this is not acceptable. Anyway, this is the memory case. This memory location with byte PTR, B at the beginning of in here, shifted 4 times, but CL is supported, so it's in a single line. This is acceptable. Yeah, that's it. Let me show you the shift in a real example. For example, 1110, 1010, or 1011. Binary. I put some value in AL, and I'm going to shift AL to the left. If you double click AL, you can see the binary version of AL in here. I load this value in here. It is EB in hexadecimal, 235 in unsigned 8-bit value. And I'm going to shift this EB 3 times to the left. What is going to happen? Let's go over to the PDF. This is my AL. Let me show it like this. This is my AL. The rightmost bit will be shift to the left by 1, and 0 will be entered to here. The most significant bit will be drop into carry flag. Okay, this is what is going to happen at every shift. Let me open this here. At every shift, for example, in first shift, it becomes D6. Value is shifted by 1 to the left. Again and again, the result is here. Let me emulate this shift in an emulate text editor. Okay, this is my number. Let's get rid of this B. What will happen? This 1 will be carried into carry flag. Let me show you like this. Carry flag is 0 at default. This 1 will be copied into carry flag. The rest of this value is in our register. Our register is now AL. The rightmost bit will be filled with 0. This is the first shift. Write it in here. This is the first shift. Second shift. leftmost bit will be put it into carry flag. Rest of this will be copied into AL. The rightmost bit will be 0. This is also another shift. And let me emulate the last one. The leftmost bit will be copied into carry flag. The left of this register copied into here. The rightmost bit will be filled with 0. So the final value is here, carry flag is 1. Let me open the example again with flags opened. I'm going to reload this. Minimize this one, minimize this one. Let me show you the inner example one by one. Okay, we have 1, 1, 1, 0, 1, 0, 1, 1. We have this value. First shift to the left, our value becomes 1, 1, 0, 1, 0, 1, 1, 0. Our value is this. And please be careful, carry flag become 1. I'm going back and forth. Carry flag is filled with 1. We are at the third line in here. Another shift, our value is here 1, 1, 1, 0, 1, 0, 1, 1, 0, 0 is here. Carry flag is 1. Another shift and the result is 0, 1, 0, 1, 1, 0, 0, 0. And the carry flag is 1. For example, if I put another shift, what will be the output? If I put another shift, the carry flag will be 0. The value will be this. Let me minimize those ones. Open the AX and flex. Okay. Second line. Third line. Fourth line. Fifth line. Please look at the carry flag. It will be zeroed after this. Carry flag is zeroed because this most significant bit put it into carry flag. Be careful, we are working only with AL. If we are going to change this code into AX, for example, it will be completely different. These bits will not drop into carry flag. Those are going to AH. Let me show you the emulator again with this opened. Okay, our value is loaded. This is our value. I'm going to shift this by 1. Please look at the AH. AH is filled with the values. By the way, carry flag is always 0. Why? Because the AX is completely shifted. The most significant bit of AX is 0 at the beginning. It keeps updating with the 0. And as you can see, the result is changed. So be careful what you are shifting. Okay, there is another instruction, shift arithmetic left. It looks like another instruction, but those are exactly same instructions. So shifting left is only one instruction. You can use any one of them. Okay. Any question about here? Okay, let's go to shift right. Shift right has two instructions this time, two different instructions. Shift right with and also shift arithmetic right. This is logical right, this is arithmetic right. The difference is the arithmetic right tries to store the signed bit in it. For example, in your example, 8-bit minus 1 in hexadecimal. What is 8-bit minus 1 in hexadecimal? It is FF, remember. This is minus 1. This is minus 2, minus 3, minus 4, goes like that. The most significant bit in here, for example, this is minus 1. Actually, this is signed 8-bit. Minus 1 in hexadecimal, minus 1 in binary. So the most significant bit in here said that this is a negative value. We know that this is signed value, this is negative. Calculator, converter, calculator. For example, minus 10. Let me show in our calculator. In programmatic. Minus 10 in hexadecimal F6, but you have to put ones at the beginning of these locations. So you have to, the sign bit in here, this is 64-bit minus 10. If you use, for example, 8-bit, this is the most significant bit. If you sign bit, sorry, if you update this value with 16-bit minus 1, this will be the sign bit. So the most significant bit needs to be stored, kept. For example, in 8-bit, we have this value. No, I'm not going to give an example about it. Okay, shift right, directly I'm going to go over here, shift right by 4. For example, we are shifting right the whole register AX 4 times. Shift right is the most significant bit will be filled with 0. The least significant bit will be dropped into carry flag. Exactly opposite the shift left. You can understand it from looking at this schema. Okay. Shift right, shift right, shift right goes like that. The least significant bit keep dropping into carry flag. I'm reloading this. The least significant bit dropping into carry flag. That's the important part. For example, if I update this with AL, it's not going to shift all AX, but just AL. But there won't be any difference because AH doesn't have any value. For example, if I put this value into AH and shift AX, what will happen? Let me show it. AH has some values. If I shift AX completely to the right, the lower bit of AH will be dropped into AL, and the least significant bit of AL dropped into carry flag. Okay, this way we moved 4 bit of AH into AL. I'm reloading this. Please look at the AH value in here. We have EB. After 4 shift right, the B value will be in AL. Please look at here. The 4 bit means 1 character. 1 character is shift to the right. Okay, this is a simple shift. Shift arithmetic right. Shift arithmetic right is when you are working with arithmetic operations. How can I say that? For example, this value, exactly same value, which is EB. EB in signed version is -21. Okay. Let me work with AH, and I'm going to use shift arithmetic right, emulate, open the values. Okay, we have -21. We are going to shift right by 4, -11, -6, -3, -2. As you can see, minus operand signed bit is kept. We know that the operations keep working on signed value. Okay, so where do we use these shifts? I'm going to say it directly. Shift left is actually multiplying. Shift right is actually division. So, in other words, shift left is multiplication. Shift right is division. Okay, it's a bit obvious actually. Let me give an example in 10 base. For example, we have 73 in decimal. This is in 10 base. Okay, when you multiply 73 with 10, what you are going to do, what you generally do, you put 0 at the end. This way you can multiply with 10 easily. Okay, you already know this. This is actually shifting 73 one character to the left, so that you have multiplied with its base. In binary, 2 base, for example, we have 2. If you shift this value to the left by 1 character, 1 digit, what is this value? This is 4. So we multiply it with the base. When we add 0 at the end of a 73, we multiply it with base. When we add a 0 at the end of a value, binary value, we multiply it with 2. For example, in 16 base, hex base, whatever you call, we have a value. If you put a 0 at the end, you multiplied it with 16. Okay? So shifting left is multiplication. If you shift 2 times, you multiply it with 100. If you shift 2 times, you multiply it with 4. Okay, we have 2. First shift, it becomes 4. Second shift, it becomes 8. Okay, so you understand the concept. Shifting left is multiplication with the base. So shift right. Shift right is actually, you can think of this. If you shift right this value, which is removing an element from the right, that value is dropped into somewhere. we divide the value into base. So if you shift right, you divide it into base. For example, we have 8 in here. This is 8 in binary. If we get rid of the rightmost bit, which means shifting right, you can understand this, I think. If you shift right this value, the value is here. This is the shift right version, and another shift right is this, and another shift right is this. For example, this is 8, this is 4, this is 2, this is 1. If you shift right 8 with 1 times, it will divide by 2 and the result will be 4. If you shift right 4, it becomes 2. If you shift right 2, it becomes 1. For example, if you shift right 1, it becomes 0. This is not exact division because the result is actually 0.5, but you can't show that value in here. So division is not exact operation, but multiplication is exact operation. So be careful. Shifting left is result in exact value, but shifting right division is may not be in exact value. Okay. I'm diving into examples. We have lost so much times. First example. By the way, is any question out there? No. First example. Write a program that multiply unsigned values 18D and the value of this memory location by using shift instruction, and saves the result to the memory address of this location. How you are going to multiply by shifting? First, let me ask the question, which shift operation is multiplication? Is there any answer to this question? Which shift operation is multiplication? Shift left or shift right? Any answer? Shift left, exactly. So we are going to shift to the left, but how many times? I have already said that shifting 1 means multiplying with 2, shifting 2 means multiplying with 4, shifting 3 times with a number is multiplying it with 8, shifting 4 times 16, shifting 5 times 32. It goes like that. 2 to the power of number is multiplication, shift number is multiplication. 2 to the power of 2, for example, is multiplication with 4. So how can I multiply with 18? There's 16, after that it becomes 32. There's 8, there's 2. How can you multiply with 18? You can't shift 4.2 or something. You have to shift exact amount of times. In mathematics, actually it didn't say that multiply unsigned value of 18 emeralds by using shift instruction. In 8086 architecture, all the calculations in hexadecimal. So whatever you write, it converts them into hexadecimal. Use hexadecimal multiplication and store the value. It's up to you using decimal or binary values in your multiplication. But try to find an answer in another base. Maybe an answer, but there's an easy catch. Let me show you to that. For example, we have a value and we want to multiply this value with 18, right? In mathematics, we have parentheses, and parentheses will be done in first. If you look at this example, these are exactly the same things. this addition operation will be done first, and then this operation is done. If you open this parenthesis without adding this value, you get this value times 16 plus value times 2. I open the parenthesis. This is the result. So we have 2 to the power of bases. This is 4, this is 1. So I can what was the value we are shifting? It's a memory address. We have a value in 1000H memory address. For example, what the value should be? Let's say value is 2. I'm going to get that value into AX. And shift this AX or AL. How many times should I shift? According to this calculation, I'm going to shift 4 times. And then shift 1 times. But shifting 4 and after that shifting 1 times is exactly doing shifting 5 times. So this is exactly same to this. So shifting 5 times is actually multiplying it with 33. How can I get rid of that? I'm going to use another variable and copy the original value, because remember these values are same. You need to shift original value, not the shifted value. So I'm going to shift the original value 4 times and shift the original value again with 1 times and add those values into, for example, AL. Okay, this is multiplying with 16. This is multiplication with 16. This is multiplication with 2. So the result is multiplication with 18. 18 times 2 is 36. AL has a value of 2. We have value at the BL again. We shift 4 times AL and shift 1 times BL. These are hexadecimal. And add them together. The result is in AL. 24 means 36 in decimal. So 2 times 18 is 36. We have found the answers. But the question wants us to work with memory directly. So let's get rid of, for example, BL. I'm going to use this memory location. And the result should be stored in where? In 1002. Let me use memory in here. Move the result into 1002, but the result is in, oops. So let's change this BL and 1000H so that the result will be in BL. Okay. What am I done? I've used a memory and a register. Oh, I use BL, not PL. We use AL. Single register and a memory combination. We have value in AL and also value in 1000H address. These are same values, original values. I'm going to shift AL by 4. So AL has the value of 20. Shift 1000H by 1. 1000H is shifted by 1 and the result is 4. And add these two locations, this and this, into AL. The result is in AL. I'm going to put that AL value into, oops, wrong location. It should be 1002 hexadecimal. It is important. Okay, this is the first question. Second question. Write a program that divides signed value of 3000H memory address by 4 using shift instruction and save the result into same location again. So which shift is a division? Which shift is a division? Left or right? Shift left or shift right? Which one is division? Any idea? Okay, shift right is division. There's no answer. Shift right is division. Thanks, Ahmet. But which shift right should I use? Shift arithmetic right or shift logical right? This is logical right, this is arithmetic right. In order to understand this, we have to look at the question. Question states that write a program that divides signed value of 3000 address. It says we have an signed value. In order to keep track of this signed value, keep this signed bit, we have to use arithmetic right. Okay, I get rid of this. We need to shift right. Which location? 3000 H location need to be shift right. How many times should I shift? I'm going to divide it by 4. In order to divide by 4, how many times should I shift? Any idea? In order to divide 4, how many times should I shift right? Within the base 2, shifting 2 is dividing 4. So I need to shift 2 in decimal. This means dividing by 4 decimal. So this is actually it. This is the second question. We have a signed value in 3000H. We need to divide it by 4. This division operation needs to be done with shift instruction, and the result needs to be in the same location. So this shift instruction directly moves the value within there. This is the answer, but let's put some value and see the answer in action. For example, I'm going to put 620 in 3000H, and I want to see the result. Okay, we have 14 hexadecimal in 4000 address. I'm going to shift right by 2. and the result need to be 5. Okay, result is 5. 20 divided by 4 is 5. Okay, this is the second question. Third question. Write a program that shifts the value of 1400 memory address to the right until the value of 12 bits will be 0. Okay, we have a value in memory location 1400. Let me put some value in 1400 hexadecimal in binary. Just because it is saying until the value of 12 bits, it means it is 16-bit value. So we have 1400 and 1401. Okay, I'm going to put a value in binary. For example, is this acceptable? No, it's not accepting spaces. Okay, we have this value, for example. We don't know. Question, example, want us to shift this value until the 12th bit will be 0. Okay, this is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. This is the 12th bit. Until this value becomes 0, we are going to shift right. How many times we need to shift? That's why we need a loop. Endless loop. Within this endless loop, I need to shift right or shift arithmetic right. One of them is memory location. By 1. Within every loop, I need to shift right or shift arithmetic right. Which one? Any idea? We are shifting right. There are ones are coming in. We need this value to be 0. We are shifting right. Which shift should I use? Logical shift right or arithmetic shift right? When you open our PDF, please keep in mind that shift arithmetic right will put the most significant bit into register again. The shift logical right is putting 0 here. So which right should I use? And so that this 12th bit becomes 0. Shift arithmetic right or shift logical right? The answer is shift logical right, because if we use shift arithmetic right, the first bit, which is signed bit, needs to keep entering the value again and again, so there won't be a 0 ever, never in here. So I'm going to use shift logical right. And I need to be said that you have to use the word within this memory location. Let me show you the value here. It is F80F. F80F. This location is 2400, and also the other location 2401. Okay, we are completely shifting the 16-bit register starting from 1400. Okay, how can I check that the 12th bit is 0 or not? At this point, you can't answer my question because you don't know the test instruction. With test instruction, this is a logical AND instruction like compare. We can use test like compare, but it only affects the zero flag, sign flag, and parity flag, not all the flags. It only affects the zero flag, sign flag, and parity flag. Operation is ending. Ending is, this is the truth table of ending. Ending is only one when the first operand and second operand is 1. So that we can understand that 2 of them is 1. We are going to test this value with some another value of a predefined value, which is whose 12th bit is 1. For example, when you test these two numbers, let me write it like this, bit by bit. Let me open the truth table for you. 1 0 0 1 0 0 1 0 0 1 0 0 1 1 1 0 0 0 0 0 0 0 goes like this. 1 0 0 0 0 0 binary. So that the result is not 0. At this way, we understand that 12th bit is 1. But let's say this bit is 0. What will be the output? Output will become 0. So that 0 flag is set, and I understand that 12th bit is 0. Oh, we need to test. We need to test first. Maybe the 12th bit already 0. Write a program, shift value memory address to right until the value bit will be 0. It didn't specifically mention that, but let's test first. Test instruction can be memory register, so that I'm going to test 1004H with AX by writing word ptr in here. It is going to test, and according to this test, it looks for the 0 flag. If 0 flag is set, which means the 12th bit is 0, so that it is going to jump, for example, to SON. Let's say here we have a label of SON. Jump, it is going to shift. So this is our code. Let's emulate and see if it is true or not. How many times is this going to shift? 1, 2, 3, 4, 5 times later, a 0 will be entered into 12th bit. So this is going to run 5 times. First shift in here, second shift is here, third shift is here, fourth shift is here, and the fifth shift. After the fifth shift, the 0 is find and jump 0 is jump. So that we have a value of 7C0. Let me put this address into, for example, BX, so that we can debug live. Okay, open the VX. Please look at here, the binary version of this value. Okay, this is our value. This is the 12th bit. Exactly this line. Okay, I'm going to test this result and look at the flags, by the way. We are going to look at the 0 flag. When it is 1, it will jump and end. So it not jump, and look at the value here. It is going to shift. A 0 is entered from the left because we used shift logical right. Okay, another test, not jump, another shift, another 0 is entered from the left. Goes like this. And remember, this was the 12th bit. This bit is the 12th bit. 12th bit is going to be 0 in here. 12th bit is now 0. At this test location, 0 flag will be set. As you can see, 0 flag will be set, and jump 0 will end the program. Okay. Any question about this third example? Okay, there's no question, I think. The fourth example. Okay. The fourth example again will be your homework. I'm not going to give a grade about your homework. I just want you to write some codes. Write a program that will find the nibbles of the value of 1000H memory address. The left side of the value will be written into CH, the right side of the value will be written into CL. Right side, left side, actually the nibbles. Let me show you in visualized form. This is 1000H memory location. Let's say it has a value of ABH hexadecimal. 1000H memory address is 8-bit. Every character is 4 bits, so this is 8-bit. Nibble means 4-bit. Nibble means 4-bit. Be careful. Question want you to put these nibbles into CH and CL. For example, A in CH and B in CL. This should be the final version of your code. Okay, 1000H, let's say, as the memory value of AB. You need to use some shift right, shift left, shift arithmetic right, something. And at the end of this code, the CH and CL value will be like this. Be careful, not like this. Okay, so CX will be 0A, 0BH. Combination of these two is CX, remember. Okay, this will be your homework. If there isn't any question, I'm stopping the recording here.